Welcome to GEMCHEM. Now today's video is on chemical thermodynamics part 8 video, and here we are going to deal with Carnot cycle and approach to second law of thermodynamics. So as requested, I started this second law of thermodynamics series, and this part is present in BSc first year syllabus, and in some cases in some universities it may be present in BSc second year syllabus. Now before starting, few things to mention. If you have noticed that on commenting, the comments are not visible in my channel. So there is a problem from YouTube. So if you have any kinds of doubt or suggestion, you can contact me through FB page, or you can also mail me at gemchem0051@gmail.com. Now, if you are new to GEMCHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. And already 7 videos are uploaded in channel on chemical thermodynamics. You can watch it. I will give the link in the description box as well as the I button present above this video. And previous videos are very essential to get continuation with this second law of thermodynamics part. So it is essential to see those videos and then come to this video. Now let us start. Now from first law of thermodynamics, which we have seen in our previous videos, we cannot predict the feasibility and direction of the process. If we are taking any kind of processes, then whether that process is going to occur or not, we can't tell that with surety. And in which direction, either forward or backward, the direction of the process cannot be determined using the first law of thermodynamics. And the 0th law, which we have known in our previous videos, there we only get information about the temperature. Now we need to get a concept of conversion of heat into work in order to approach to second law of thermodynamics, and this conversion is best explained by the tool which is known as Carnot cycle. Now this Carnot cycle, from the word you can understand that cyclic process is involved, and Carnot is the name of the scientist, and reversible, that is, since it is a cycle, each and every step is reversible, and here working substance must be ideal gas. So basically, while learning about the Carnot cycle, we will consider ideal situation, but in actual cases, when we go to different real cases, then this Carnot cycle is not considered, because when we will see the different calculations involved in the Carnot cycle, then we will get that the efficiency of the Carnot cycle is 1. But actually, in case of real world, this efficiency is always less than 1. And this must be understood in this whole concept of Carnot cycle. Now, the 4 steps of Carnot cycles are isothermal, reversible, expansion. Now, what is isothermal? We have already seen. Again, you have to know it. That is constant temperature. Reversible means that the process is in the same rate in the forward and the backward reaction. Expansion means that is expansion of volume. And second step is adiabatic, that is no heat or mass or energy exchange. Next one is reversible expansion. So adiabatic, reversible, expansion. Third step is isothermal, reversible, compression. And the fourth step is adiabatic, reversible, compression. First we are expanding the system, first we are increasing the volume of the system, and next, in the next 2 steps, we are decreasing the volume of the system by compressing it. Each and every step has different works involved, and these works and the energy which it takes to do that work will be needed to get the efficiency, and we will calculate the work done for each and every step. These work done calculation will be shown in a compressed manner, as for each of these cases we have already taken out by deriving the equations in previous videos. So let us see how to get that. We will directly use the formulas for isothermal, reversible, expansion and compression, as well as adiabatic, reversible, expansion and compression. So let us see. Now first we need to understand the system which is being used in a Carnot cycle. So in Carnot cycle, we are using a source which is higher in temperature than the sink which we are taking. And an engine is being involved in between, which takes up a heat of Q2, which is absorbed by engine from source at T2. And then it does some work. So some amount of work is being released, which we can tell as W, which is our work being released, and this Q1 is the leftover heat which is dumped into the sink, and the temperature in the sink is T1. So we can tell this source as high temperature reservoir and the sink as low temperature reservoir. Now we will see each and every step here. Now if you consider this is the system with a pressure of P1 and V1, then on first isothermal reversible expansion, there will be a decrease in pressure and increase in volume. So as you can see, the piston has gone up. Next, we are keeping it in a insulated manner for undergoing adiabatic reversible expansion. So this system will undergo again expansion under adiabatic condition to give us another system which is C, and here the pressure is P3, V3. Next, it will be taken out from this insulated system, and this C is then being made to undergo through isothermal reversible compression. Now as you can see, on compressing, this piston has gone down and the volume has been decreased from V3 to V4, and the system is now D. And ultimately the last step, in which if we perform the A2 step, that is A2, that is adiabatic reversible compression, then we will see that it will return to the A system. So first we are expanding up to this one, then we are again compressing the system for these two, right? Now we will see the graph, that is P versus V graph for a Carnot cycle. Now we have already discussed the adiabatic curve as well as the isothermal curve. So if you remember, then isothermal curve is like this and adiabatic curve is much more steeper. So first process is our I1, that is isothermal expansion. So here from this pressure, the pressure is getting decreased and the temperature remains constant. Here also it is T2. Whereas the volume is increasing, as you can see, graph increases this side, whereas pressure increases this side. So this is the first step. Next is A1 step, where we are involving a BC line which is much steeper than the isothermal curve. So here we can see that from P2 to V2 it is going, and since there is an expansion, so volume is increasing whereas the pressure is decreasing. Now it will undergo compression. So in compression, pressure will increase. It is increasing from P3 to P4, whereas the volume is decreasing and going from V3 to V4. It is going in the decreasing side, and the temperature in this case remains constant. Similarly for DA, this curve is steeper and this is for compression, and here we can see that the volume V4 and V1 is different. V1 is smaller than V4 as compression is occurring, whereas P4 is lesser than P1. So P1 is greater pressure, so it is going in under greater pressure. Pressure is increasing. Now if we come into the concept of Q2, then for this isothermal part, there is an entrance of a heat which is Q2, and in this isothermal compression part, Q2 is converted some amount to work and the leftover part is being released as Q1, and this part is important. This is the main flow chart of Carnot cycle. If you want to draw this, the exclusive part which you should ignore is that do not use these arrows. Only draw here like this arrows. These arrows will be sufficient and others will be remaining same. So just try to ignore the blue arrows, right? Now we will go for the next part. Now we will see the works involved in each step. So we will first do for step 1. Now in step 1, since it is a isothermal reversible expansion, so W1 is minus Nr and the temperature is T2 ln. Since we are going from V1 to V2, so final volume by initial volume. And since it is an isothermal process, so our internal energy change is 0. Q2 plus W1 gives us delta U1, right? So in this case, our Q2 is coming as nRT ln V2 by V1, and this is the heat absorbed, right? Now we will see for the step 2. So if we see step 2, in this case there is no involvement of heat, so here Q equals to 0. Next comes, since it is an adiabatic process, so U2, delta U2 must be NCV and the final temperature minus initial temperature. So from this formula which we have seen, Q plus W2 equals to delta U2, here we get W2 equals to NCV T1 minus T2, right? Now for step 3. So for step 3, we have W3 equals to minus nRT. Again, since it is a isothermal reversible compression, so here the temperature will be T1 ln V4 by V3. Since it is an isothermal condition, so U3 must be 0. So we get Q1 equals to nRT1 ln V4 by V3. For step 4, we get again Q equal to 0. Delta U4 is NCV T2 minus T1. Here now the final temperature is T2. So we get W equals to NCV T2 minus T1. Next work is to calculate for the whole cycle. In the whole cycle, what we have got? So delta U for the whole cycle, if we calculate, then we have to calculate delta U1 plus delta U2 plus delta U3 plus delta U4. Here delta U1 is 0 plus NCV T1 minus T2 plus 0 plus NCV T2 minus T1. Ultimately, we will get it as 0. Next, we will calculate for W, right? So here, it must be W1 plus W2 plus W3 plus W4 minus nRT ln, here T will be T2, V2 by V1 plus NCV T1 minus T2 minus nRT ln V4 by V3 plus NCV T2 minus T1. From here, this 2 gets cancelled. what we get is W equals to minus nRT to ln V2 by V1 minus nRT1 ln V4 by V3. We know that for adiabatic reversible processes, that is BC and AD, BC if we consider, for adiabatic reversible, remember, T2 V2 gamma minus 1 equals to T1 V3 gamma minus 1. Similarly, for AD we can write T2 V1 gamma minus 1 equals to T1 V4 gamma minus 1. From here we get V2 gamma minus 1 by V1 gamma minus 1 equals to V3 gamma minus 1 by V4 gamma minus 1. What we are doing? We are just taking the ratio of T1 by T2 so that it becomes same. Next step is this one, that is we will ultimately get V4 by V3 is equal to V1 by V2, and we can write W equals to minus nR T2 minus T1. If we substitute here V4 by V3 with V1 by V2, then this will become minus nRT1 ln V1 by V2, right? And if we want to just make it reverse, then this becomes, sign becomes plus, and we get ln V2 by V1. So since this sign becomes plus, when we take a minus common, then it becomes minus and this becomes plus. Just try to solve it, then you can understand. Ln V2 by V1. So this is our work, right? This is our work obtained. Now we will take out the efficiency. So let us see. Efficiency will be like this. That is, eta is the representation for efficiency. It is equals to W by Q2, since Q2 is given heat. We have obtained W as nR T2 minus T1 ln V2 by V1 by, we have already got the value of Q2, right? So it is nRT2 ln V2 by V1. Now what gets cancelled is this term as well as nR. What we are left with is T2 minus T1 by T2, which is equals to 1 minus T1 by T2. This is the value, and this value is important. So efficiency comes to be about 1 minus T1 by T2. That's why it is written that efficiency is only dependent on the temperature of source and sink. It is not dependent or nor on the amount of substance or nature of gas. And this W can be obtained as Q1 plus Q2. If you see the value of Q1, this is the value of Q1, and what is the value of Q2? This is the value of Q2. So if you add this two, then you will get the value of W. This one you will always get. So that's why we can write it as that W is equals to Q1 plus Q2. So this was important concept of Carnot cycle. Now this is the checkpoint. Try to draw the Carnot cycle on VP diagram, that is volume pressure diagram. We have already drawn pressure volume diagram, that is PV diagram. But you have to draw in VP diagram as well as HT diagram and UT diagram. H is for enthalpy and U is for internal energy. Using the datas of previous videos on enthalpy and internal energy. Hope you can draw this. If you can't, in the next video I will help it out. So this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe, and on the commenting part, please do understand that if any problem comes, comment on Gmail or Facebook page. Right.